Quantum entanglement is one of the most bizarre and intriguing phenomena in the realm of physics. It describes a strange connection between two particles, where they become linked, even across vast distances. This link is so powerful that the fate of one particle instantly influences the fate of the other, no matter how far apart they may be. Imagine two coins flipped simultaneously, one always landing on heads and the other always landing on tails. This coordinated outcome, while peculiar, hints at the essence of entanglement. This spooky action at a distance, as Einstein famously called it, challenges our everyday understanding of the universe. In our classical world, objects interact through direct contact or forces that travel through space. Entanglement, however, suggests a deeper, more fundamental connection between particles that transcends the limitations of space and time. This concept isn't just a theoretical curiosity. It has profound implications for our understanding of the universe and is paving the way for revolutionary technologies like quantum computing and communication. To grasp the full significance of entanglement, we need to delve into its historical roots and explore the experiments that have confirmed its existence. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that would become a cornerstone in the debate about quantum mechanics. Known as the EPR paradox, it challenged the completeness of quantum theory by highlighting a seemingly impossible consequence of entanglement. The paradox centered on the idea that if quantum mechanics were a complete description of reality, it should be possible to know both the position and momentum of a particle with absolute certainty. However, Heisenberg's uncertainty principle, a fundamental tenet of quantum mechanics, states that it is impossible to know both of these properties simultaneously with perfect accuracy. The EPR paper proposed a thought experiment involving two entangled particles. If these particles were separated by a large distance and a measurement was made on one particle, the properties of its entangled partner would be instantly determined, even without a direct measurement. This instantaneous correlation, they argued, implied a spooky action at a distance that contradicted Einstein's theory of special relativity, which prohibits information from traveling faster than light. The EPR paradox remained a thought experiment for decades, fueling debates about the nature of reality and the completeness of quantum mechanics. However, in 1964, physicist John Bell formulated a groundbreaking theorem that provided a way to experimentally test the predictions of quantum mechanics against the principles of local realism championed by Einstein. Bell's theorem proposed a set of inequalities that, if violated, would prove the existence of entanglement and the non-local correlations it implied. These inequalities essentially set a limit on the correlations that could be observed between two particles if they were only influenced by local factors, meaning factors within their immediate surroundings. In the following decades, numerous experiments were conducted to test Bell's inequalities. These experiments, often using entangled photons or atoms, consistently violated Bell's inequalities, providing compelling evidence in favor of quantum mechanics and the reality of entanglement. To understand the mechanism behind entanglement, we need to delve into the heart of quantum mechanics, the wave function. In quantum mechanics, a wave function is a mathematical description that encompasses all the possible states of a quantum system, such as an electron or a photon. Before a measurement is made, a particle exists in a superposition of states, meaning it simultaneously occupies all possible states described by its wave function. When two particles become entangled, their individual wave functions become intertwined, forming a single shared wave function. This shared wave function describes the combined state of the two particles as a single entity. Consequently, the act of measuring one entangled particle instantly collapses the shared wave function, forcing both particles into a definite state. This collapse of the wave function doesn't involve any physical interaction or exchange of information between the particles. Instead, it's a purely quantum phenomenon that transcends the classical notions of space and time, leading to the instantaneous correlations observed in entanglement experiments. Section 5: Quantum Entanglement in Action, Real-World Applications. The bizarre nature of quantum entanglement, once relegated to the realm of theoretical physics, is now being harnessed for practical applications with the potential to revolutionize various fields. One of the most promising applications lies in quantum computing. Quantum computers leverage the principles of superposition and entanglement to perform calculations that are impossible for classical computers to handle. Unlike classical bits, which can only be either a 0 or a 1, quantum bits or qubits can exist in a superposition of both states simultaneously, thanks to the principles of quantum mechanics. By entangling qubits, quantum computers can perform computations on multiple possible values simultaneously, exponentially increasing their processing power for specific tasks. This ability opens up new avenues for drug discovery, materials science, cryptography, and artificial intelligence, where complex problems that would take classical computers years, if not centuries, to solve could be tackled in a matter of hours or even minutes. Section 6. A philosophical crossroads, entanglement's implications. The implications of quantum entanglement extend far beyond the realm of practical applications. It forces us to confront profound philosophical questions about the nature of reality, the role of the observer, and the fundamental interconnectedness of the universe. One of the most unsettling aspects of entanglement is its challenge to our intuitive understanding of locality. The idea that two particles separated by vast distances can be instantaneously linked challenges our classical worldview, where information and influences are limited by the speed of light. It suggests that the universe might be fundamentally interconnected in ways we are only beginning to grasp. Furthermore, the role of the observer in quantum mechanics takes on a new significance in the context of entanglement. The act of measurement doesn't simply reveal pre-existing properties of entangled particles but actively participates in shaping their fate. This entanglement-driven measurement problem raises questions about the nature of objectivity and the role of consciousness in shaping reality. Section 7. Confirming the unthinkable experimental validation. The theoretical framework of quantum entanglement has been rigorously tested and confirmed through numerous experiments over the past few decades. These experiments, often pushing the boundaries of technological ingenuity, have provided compelling evidence for the reality of entanglement and its non-local correlations. One of the most notable experiments was conducted by Alain Aspect in 1981. Aspect's experiment used entangled photons to test Bell's inequalities with unprecedented precision. By carefully controlling the polarization of entangled photons and measuring their correlations, Aspect's team demonstrated a clear violation of Bell's inequalities, providing strong support for quantum mechanics and the non-local nature of entanglement. More recently, in 2017, researchers at Delft University of Technology in the Netherlands conducted a landmark experiment that closed several loopholes that had plagued previous tests of Bell's inequalities. By entangling electrons across a distance of over a kilometer and ensuring strict space-like separation, the Delft experiment provided the most robust confirmation of entanglement to date, further solidifying its place as a fundamental aspect of the quantum world. Section 8. Unraveling the mysteries, challenges, and open questions. Despite its experimental validation and growing list of potential applications, quantum entanglement remains one of the most mysterious and perplexing phenomena in physics. While we have made significant strides in understanding its properties and implications, several fundamental questions remain unanswered. One of the biggest mysteries surrounding entanglement is the mechanism behind its instantaneous correlations. How do entangled particles communicate with each other across vast distances without violating the speed of light limit imposed by Einstein's theory of relativity? This question lies at the heart of the debate between quantum mechanics and our classical understanding of the universe. Another open question is the role of entanglement in the emergence of classical reality. Our everyday world seems to obey the deterministic laws of classical physics, where objects have definite properties and interactions are local. How does the bizarre non-local world of quantum mechanics, governed by entanglement and superposition, give rise to the familiar classical world we experience? Section 9. The universe's embrace, entanglement, and interconnectedness. The discovery and subsequent confirmation of quantum entanglement have profoundly impacted our understanding of the universe, revealing a reality far stranger and more interconnected than we ever imagined. It suggests that the universe is not a collection of isolated objects but rather a vast, interconnected web of relationships, where the fate of one particle can be inextricably linked to the fate of another, regardless of the distance separating them. This interconnectedness, hinted at by entanglement, resonates with ancient philosophical ideas about the unity of all things. From the interconnectedness of all beings in Buddhist philosophy to the concept of a unified cosmic consciousness in various spiritual traditions, the idea that we are all part of a larger, interconnected whole finds a surprising echo in the heart of modern physics. As we delve deeper into the mysteries of entanglement, we may uncover even more profound connections between the microscopic world of quantum mechanics and the macroscopic structure of the universe. Perhaps entanglement holds the key to understanding the emergence of space-time, the nature of dark matter and dark energy, or even the very fabric of reality itself. The journey into the heart of entanglement is a journey into the heart of existence, a quest to unravel the universe's most closely guarded secrets.